Genetic algorithms. How can anything improve through random mutation? Well, nature has been doing that since life began. So life has evolved through random mutations, and they cause genetic change passed from generation to generation. Most of those genetic changes, those mutations, are harmless. Some are quite harmful, and a few are improvements. But think of you sitting out in the hot sun with an incoming ultraviolet proton hitting your DNA and destroying part of a gene. So that's mutation. There are four elements to the genetic algorithm. One is the actual mutation. Second, if the organism lives to reproduce, then they select themselves through mating. Then their children inherit those mutations, and those mutations are kind of a recombination of various mutant genes from one parent and the other. So let's look at mutation in action. This is a genetic algorithm to emulate or to evolve walking behavior. And there's a starting configuration. You're looking at a side view, but it's a little sort of a robot. Sort of a square body, 4 legs. Each leg has a hip joint and a knee joint. And 4 of these random mutant kind of compete against each other at a time. What matters is how far they have traveled from their starting point in each generation. So let's see what that looks like. So here's mutant number 6, and kind of flailing arms and legs like a newborn baby would, without any attempt to go anywhere or do anything without any coordination. One after the other is like that. So in each generation, the 2 that proceed the least far are dropped, and the 2 that go the farthest have their genes mixed, and 2 children from them replace the 2 losers. And it's repeated each generation. There is no learning within a generation. The only learning happens with the random mutations between generations. Let's look at what happens after 6 hours of machine-generated mutation. So you'll see that here's mutant number 10. Look at those 2 front arms. Look at the purposeful dragging. It looks like there's actual intent and strength and tension there, doesn't it? Now, some mutants are deeply harmed by their mutation, like number 13 here. It managed to go in a circle, sort of. Not ideal. Mutant number 12 has learned to hop. Not quite good. So the rules of the game is that none of these robots had a goal. None of them were trying to do something. Just random genes changed their behavior, some good, some bad. All of the leg movement and the coordination were done by each mutant. So the coordination in this one is amazing in mutant number 11. Really, really wild. But one of the features of genetic algorithms is that the variation is maximized. It doesn't just go better, 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 better. It goes better, 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 worse, 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 both of them together. Let's look at the same idea, but with a humanoid, in this case 20 mutants, 13 joints, each with random values. And we're going to measure not only how far the mutant travels, but how high his head is, because we don't want to reward him for crawling and rolling and that sort of thing. And we measure the number of real steps, so he's not rewarded for hopping and skipping and jumping. The mutants don't know about gravity. Let's see what it looks like. Count the steps. There's not even 1 step for the first generation. Let's look at the second generation. There's sort of a little hop there. Again, not even 1 full step. But let's look at what happens after 1,000 generations. Count the steps. 1, 2, 3, 4, 5, 6, 7, Okay, let's look at the next. 1, 2, 3, 4, 5, 6. Okay. So, this system is the Genetic Walkers website from Red Newt. And it's great for kids because there's control and information. So notice the control. The students can control how often the genetic mutation happens. What's the probability for each mutant? How severe is the mutation? And how many of the winners should be used as the gene providers for the next generation. The statistics collected during each generation are amazing. You can learn an amazing amount from them. So in this case, there are 2 parents, and they're the ones in tan. And the current generation is just an alphabetized list of made-up names. And you can see the score. They're pretty high compared with the others. Most of the genetic mutations aren't as good as the parents, but 2 of them circled in green are better than one parent. But some of them are much worse. Look at the 2 circled in red, where they can't even take a single step, and that's after 1,000 generations. One mutation can cause terrible damage and death, or can really boost performance, as we can see in the record history. So to the right, the table is the list of high scores, the 20 highest scores, and the generation in which they happened. Notice, this is no steady evolution. So between generation 94 and 97, the score almost triples. That means there was one random mutation that massively changed their walking ability, made it 3 times better than it was before. And then for 100 generations, there's not much change. And then suddenly there's a 100-point gap, 100 points more, 100 points more. But look at the last 2. So in generation 455 to generation 874, that's 400 generations. There is no new high, there's no improvement. It goes 400 generations without an improvement before finally there's one that jumps to 100 more points. Wow. So this is an awesome website for students to learn how to think about genetic mutations. So this is not as cool looking as humanoid mutations, but it's also an awesome site for kids to learn. This is the NetLogo site, and it's the simple machine learning model. So from left to right, there are 3 first generation, second generation, and third generation of what starts with 25 agents clustered in the center, each with random directions, random ways of moving. And they go through 25 of their steps, and that's the end of one generation. The little red circle is the not a target exactly, but their fitness is measured by how close they are to that. So you see generation number 1, nobody's close. Generation number 2, more close. By generation 3, they're starting to cluster around that red circle, just in 3 generations. Wow. The cool thing, though, is that the code is accessible. So here I've copied the entire code for mutation. And you can get it from reading just one line, the one that in the middle that says set strat. So the strategy string or variable will have one of its items replaced randomly from a selection from a bunch of inputs. So that's a number. So a 10 may be replaced by a 1. The second one has maybe a plus sign will be replaced by a division sign or by a heading. So students can modify this, they can learn from it, they can create their own improvements. It's an awesome site created by Uri Walensky, student of the famous AI pioneer Seymour Papert. So after 100 generations, here's what it looks like. The image in the top left was generation 1. You saw that already. After 100 generations, you see none of the zigzaggy craziness is left, and more of the images are aimed toward that top right sort of code. But it also graphs the fitness. So check out the graph. That's over 100 generations. And after about 12 generations, there's no improvement. It just goes up and down randomly. So this is an example of a genetic algorithm that improves as far as it can, and that's it. So once again, it's a great playground for students to learn the ins and outs, how to think about genetic programming. So there are real-world applications for this, all sorts of engineering, routing paths for telecommunications, for the Amazon package to your door, for trips that you may want to make, for encryption and code breaking, genetic and molecular work, finance, even generating puns and jokes. Holy cow. So big ideas here are that genetic algorithms are loosely based on the successful model of biological evolution. It's a way of optimizing some value, some strategy that you have, but it actually gives you better and worse performance. It's much less data intensive. You don't need any massive source of database, huge data set. You just collect the data at the time from each generation, and you use that to randomly mutate for the next. There are wonderful tools for students to explore this model, and there are serious real-world applications. Where can students get this? Well, Brev is a great system. That's the one with the four-legged robots. It's an old system, though. It'll still work on some Windows, Linux, and Mac machines. Not a chance for a tablet or a Chromebook. The genetic walkers will work on any system because it's HTML5, any tablet, Chromebook, any computer. NetLogo similarly will work on any computer. There's a web-based version for the Chromebooks and the tablets, and a downloadable version if you want extra capability on a laptop. Awesome stuff. Hope you try it.